So we're good to go?
Yep.
Hopefully my team's online. So we are Hot Pow. I'm Jeremy Johnston. I'm a graduate student over at George Mason University. And we worked on a bunch of different things with thermal data. So let me jump over to our workbook here. And so this is our main Jupyter notebook. Our GitHub link is right here. That's where I started off. So I'm going to kind of run us quickly through our README file so you get a sense of what we were working on. And so we really were taking all the different temperature data inputs from SnowEx and beyond, and we were trying to kind of integrate these things together, come up with some cool visualizations. You know, we had a bunch of, you know, really kind of people at different places, so we got to learn a bunch of different things. And we had a kind of a great team of people who really helped make that happen. So I want to shout out all my team members here. They all did awesome work, and especially, you know, Friedrich and Stephen for helping kind of organize and orchestrate this process, because this was my first hack week. So like I said, our goal here was to kind of look at how we can pull all these different temperature data sets together. Kind of an example of that is looking at Met station data. So kind of these time series data and matching it up with pit temperatures. So these are just an example of surface pit temperatures against that Met data. You know, here's just kind of an example data frame. And to get a sense of some of the different types of scales we were working with here, this is kind of all the pits plotted. This has been a bunch of pits plotted on top of an IR image. And so we took this project a bunch of different directions, and I'm going to try to be brief so my team members can kind of talk about what they were working on. But we did kind of broke it into two kind of parts where we're looking at kind of aggregating data and wrangling data. And then we tried to extend that to a few science questions here. And we'll get into these in a little more detail. But for example, we're looking at things like how different, so even reanalysis data, how that might compare with snow pits, how that might compare with the actual ground observation time series on the ground. So we used a ton of the different tutorials and, you know, a bunch of the great information from the week. So actually, let me introduce this real quick. So again, we were kind of doing this multi-scale analysis, right? So we have people in the pits kind of taking our point observations, and then we have, you know, things like aircraft that can get a bigger region, but then, you know, it kind of pales in comparison to things like reanalysis or satellite data that can give us that kind of global perspective. So tying all this together sometimes can be challenging. And so I'm going to let my team take over.
I can give a quick introduction to, as we move through this multi-scale analysis, first we'll focus on some of the snow pit data. So here's a plot of all of the snow pits, surface temperatures from the snow pits dug during the intensive campaign. And as we can see, and as we all know from this week, there are a lot of data, and actually the temperatures vary quite a bit over the 3-week campaign. So we wanted to delve a little bit further into what some of the data sets looked like, which I think Stephen will show us below.
Yeah, so that map gives a good idea of the spatial component of all this temperature data, but here's sort of a snapshot of both space and time, except instead of looking at a map here, the y-axis is depth beneath, or the height of the snow layer. So this is beneath the snow surface, measuring temperature over time. You can see individual points at, you know, the instantaneous temperature measurements at each snow pit, and then some continuous measurements that were made at some snow pits. So it's a pretty rich data set in space and time and depth.
And so with that, we kind of felt inspired by what we saw from Stephen's previous work that he showed us both in his tutorial and in our breakout groups. And a handful of us that were pretty new to Python and Jupyter Hub and Git decided to get together as we saw other teammates producing beautiful maps quickly and figuring out these amazing complex problems. We decided, let's try and expand the data set a little bit. One of our teammates, Jewell, had an extensive set of a longer time series of snow pit temperatures. And so we decided that we would try to integrate that into the SnowEx style database and try and reformat it and get it to work so that we could also kind of look at those temperature changes over a longer period of time.
So, and before Ajay gets started with some of the data wrangling that he did, and also the visualization that he came up with, which is great. Just to briefly summarize, the pits that I dug were from March to May, after the quarantine sort of ramped up and I found myself on Grand Mesa and decided to stay and just dug a bunch of snow pits. And while I didn't have the classification of that the intensive campaign had, I generally dug pits either in the open or in the trees, and aiming for AM and PM. So I sort of segregated things that way, which I think will help explain some of what Ajay will show us.
Okay, so here, yeah, from the wrangling stuff, it was a good experience coming with a background of R into Python. But overall, we were able to read the CSV files and try to, first just rather trying to do the wrangling in terms of intake and how to append multiple CSV files, and then telling a story, first looking at the analysis of how it's in the daytime versus the nighttime. How does the temperature vary across these snow depths? And so this was for a period of approximately 3 months. So that's what we see first, and open and morning and evening. And then here we look at how it varies between the open sites and tree sites. And then this was kind of something which expected, and Jewell can explain a little bit more about what the expectation was here.
Yeah, so this is the fun HV plot that that Ajay developed, but as we can see in the mornings, the temperatures in the open, that blue line there, are a bit more negative than you might find in the trees, the red, for the most part, which we could consider with the different energy balance components in those environments. And if we can scroll down to the next plot, this is an integration then of these snow pits with the intensive campaign snow pits, which is a great opportunity to look at snow temperatures over time from the winter snowpack in February, and then as things warm and ripen in March and April. And we look forward to being able to explore these data sets with the other variables measured as well, and just want to let everybody know that these data sets will be available with the SnowEx data sets as well. So some of the takeaways from this initial snow pit analysis is just that those of us that were newer to Python and Jupyter and whatnot had a lot of fun integrating the data from the different sources, and just wish we might have had another week or two to utilize the Hackweek tools and the SnowEx data to work on together. And yeah, I think that wraps up some of what we wanted to look at here.
So moving on to the thermal infrared imagery. So just really briefly, I wanted to share this visualization. So this is airborne thermal infrared overlaid with snow pit locations, and they're both colored by temperature. And it's worth noting that these aren't exactly comparable due to the time difference between the measurements, as well as the underlying physics of in situ versus remote measurements, which again, Stephen does a really great job of describing in his tutorial. So the interesting part that I wanted to talk about, and something that I learned how to do this week, is that this HV plot is generated from 2 different data structures. So the thermal IR data set is held in an X-ray data array, and the point data is contained in a GeoPandas data frame. And I'm actually using GeoViews for the image data, which is built on top of HV plot. And it's designed for gridded data sets like model outputs and other things. So they share the same asterisk layering syntax. So you can plot using both libraries on the same map, which is super cool. And the advantage of using GeoViews is if you pass it a 2-dimensional data array, it'll plot without any additional arguments, although it does need to have the correct CRS. So again, you can do this with just a few lines of code, which is really cool, and definitely has a lot of utility for bringing together these disparate data sets like we've all been doing this week. The only downside of GV and HV plot is that I found it a little challenging to debug some of the plotting errors because of just how simplistic the plotting calls are. So I'm not sure if other folks had that experience, but I still think this is a super cool use case.
This plot here is just showing that Giulia and I were able to expand on the thermal IR imagery from the aircraft, bringing in a time series of images as the airplane flew overhead over the course of the morning. This is looking at February 8th and comparing that to some of the ground data.
Okay, and I'll jump in here. I think we have only 5 minutes left. So I'll go over this quickly. There are a couple links to the ERA5 data put together. It's a modeled global data set with tons of really cool variables. That first link right there will take you to a variable list put together by the Copernicus Climate Change Service. And we pulled in this great gridded data set for a number of variables listed at the just above that plot right there, 2-meter temperature, snow albedo, density, depth. Many more things could be pulled in, but one objective was just to get a handle on their API, pulling this in and comparing it to SnowTel and SnowEx data. So the data products are at an approximately 11-kilometer grid size cell. That's one thing to note. Here's an example of what an API request looks like to their API, and it's rather simple. It's a dictionary of basically what you want: file format, variables, time, bounding box, and your output file name. So pretty simple. Moving on, here's just a quick gallery of those grid cells over Grand Mesa. So the next plot shows us the outline of the mesa and kind of the first timestamp there in the data that we requested for temperature variance over the mesa. Here are two of the SnowTel sites, and thank you to David with that SnowTel tutorial. It's really easy to adapt and work with the SnowTel data from that. So moving on, we then compare temperature, SWE, and snow depth at those two sites from SnowTel to ERA5. And yeah, well, let me talk about briefly. Temperatures line up, and it looks like there's some kind of bias error between the SWE and the snow depth products, but the general trends kind of align there too. Okay, moving on, here's pulling in the snow depth data. Where are they? Next plot. So these are all the snow pit data. So those are all the snow pits. And then I took the mean snow pit temperature for all the pits and all the depths and compared it to the mean sampled ERA5 data. And again, the trend roughly lines up, but as we would expect, the snow pit or the snow is a bit warmer than the surface temperature that was happening during this time frame. And then Jeremy.
So I'll be super quick because I already spoke, but I tried to pull in a few extra in situ sites that I had access to and see if I could pull them in. I'm pretty new to Python, so doing that took some time, but I added 3 additional sites and was trying to compare them in the time series. I also then tried to compare across different of the cover classes of the snow depth and whether it's sparse tree cover, treeless, dense cover. And this is essentially just comparing the mean pit snow surface temperatures to nearby sites' air temperatures. And so, IR temperatures. So we actually see that the air temperatures are closer to what we measured near the surface. That's the main thing there. And the last thing I did was to try to integrate with some of the stuff Friedrich was doing, was try to overlay kind of all this information together. So this is the ERA 2-meter temperature in the black line, all the different kind of in situ sites that were on the mesa there, at least a few of them, and then also the snow pits. So again, taking that kind of integrating these different data sets together. And I'll skip the takeaways and let someone else take over here.
Yeah, so I'm just very briefly going to show another sort of more scientific application that we looked at with that data. So I'm inspired by Steven's awesome tutorial on IR imagery. And here I took this imagery to sort of think more about the spatial and temporal variability of the temperatures that we're seeing there. And so in this plot, you see in the 2 rows, 2 points in time. And you have an open grid cell and a forested grid cell. For comparison, it's like 500 by 500 meter areas. And what's interesting here, obviously, is that you get a lot more spatial variability in the forest. And that's not just because you have mixed pixels with vegetation and snow, but also because the snow temperature itself varies based on where the shadows are. This is like nicely shown in a morning image compared to a midday image. And if you slide down to the next plot, this is showing histograms of the 4 panels that you just saw. And what I find really interesting about these plots is that the shape of the histogram that you have in the forested scene also changes in time. And this is sort of something to think about when we're looking at mixed pixels and when we want to use this data for validating models. So yeah, certainly something that I'm taking away from playing with this data this week. And I hand over to Wenge for the final.
So I was really inspired by the thermal image, this spatial variability, and particularly looking at the impact of vegetation structure. Can you hear me? Okay, so I think the idea is we have this kind of really transfer model, which we can simulate the shadow component, shortwave radiation transmission, long wave transmission. So for this application, I'm particularly interested in integrate the LiDAR structure data through the radiative transfer model, so we can predict the shadow component. So for this project, what I did is we run this PyCront tree segmentation algorithm. We were able to segment the tree so that you can see this one is showing the size of each tree crown. So hopefully we are doing right now is just integrate the size of this crown information into our canopy radiative transfer model, calculate the shadow component, shortwave radiation, energy balance, all related snow melt, the energy balance stuff. So that's just still going on. And unfortunately, I couldn't really get the point cloud data for Grand Mesa. So this one is running on one of the site, a neon site in California. So this tree segmentation approach.
Awesome. So yeah, we really brought together a lot of different things here, and I wanted to kind of touch on a few kind of overarching takeaways. We all kind of use the SnowEx SQL database, and it was a real lifesaver, especially for working with the snow pit data. That was awesome. And again, we want to thank all these great tutorials. I'm sure all of us use them in different parts of this, but especially the HV plotting and some of the airborne stuff. And so again, there's tons more applications here. We only had so much time, but we came out of this with a lot of new ideas as well. So thank you.
Okay.